In this video, we will discuss the background for the chapter on numerical integration, and we will do so by looking at some examples where the definite integral plays a part, and also showing why numerical integration is often necessary. So, integration is a topic that you've all seen in calculus, so I'm assuming that all of you have a usable knowledge of what integrals are, how to compute integrals of basic analytical functions. But I want to take a step back here and actually look at what does an integral actually do. Now, the entire idea of an integral is to combine infinitesimally small parts of information on a function into aggregated or integral quantities. And a primordial example of such an integral is when we try to compute the area below a curve. So that's what we see over here. So we have our function y is f of x, this blue line, and over the interval between x is a and x is b, we want to compute the area between the curve and the x-axis. However, unfortunately, well, we do not know how to compute areas of a general shape. We know how to compute this, for instance, for a rectangle, for a triangle, for a trapezoid, but for a general function f of x, we have no general solution how to compute the shape of that using only a simple formula. So therefore, what we do is, well, we cut up the interval from a to b, so the interval of x from a to b, we cut this up into small subintervals. In this case, n intervals of a width of delta x. Now, in each of these intervals, we will try to approximate the shape of which we want to compute the area by a shape that we know how to compute the area of. And for instance, we can do this by drawing rectangles. And we see over here that we can draw, in this case, 4 such rectangles. And the area of such a rectangle is easy to compute because, well, this is a rectangle. The area is base times height, or width times height. So the height here, well, that's associated with the function evaluated somewhere between x1 and x2. And here we just take the function evaluated at x1. And the width is delta x. And we can do this simply for each of these rectangles over here. So this gives you a formula for the dark blue area over here, where we have chosen ci is equal to xi. But you could also choose it to be xi plus 1. And then these rectangles, well, this one would have a height up until here, and this would be the rectangle. But that's of little importance now. So this allows us to approximate the light blue area with these dark blue rectangles. And the end goal is, well, to compute this light blue area, and we can do so by summing up these individual areas here by letting this number n, the number of subintervals, go to infinity, because then these delta x will get smaller and smaller and smaller. The blue, dark blue rectangles will start approaching our function f of x closer and closer and closer. And in the limit of n going to infinity, the area of the dark blue rectangles will be exactly equal to the light blue area below our function f of x. And we can do so, well, we just compute the sum of all these small areas, delta A. We let n go to infinity, and this is what we call a Riemann sum. And from calculus, you know that such a Riemann sum can be evaluated using a definite integral. So this actually shows you that the area below this curve, below the curve y is f of x, is equal to the definite integral of f of x between a and b. So that's the first application of the definite integral. Let's look at the second application now. So instead of computing the area below our curve y is f of x, let's actually compute the length of the curve itself. And again, we know how to compute lengths when we have straight lines. Then it's easy to compute the length. But here we have this, well, curvature, which is governed by properties of our function f of x. So we have no general closed form, easy computable formula for this length L for a general f. So again, what we need to do is, well, we need to cut up our big problem into small problems that we know how to solve. So again, the first thing we do is, well, we partition our interval into n subintervals, where here we use 4 subintervals, but you can use more and more. And within each of these intervals, well, we basically approximate this curve itself, the curve itself, so not the area as in the previous case, but the curve, well, we approximate it using, well, using this triangle over here. And if we investigate this triangle, well, we see that the width of such a triangle, well, that's simply our spacing of the interval, delta x. We know that the height of this triangle, well, that will be the derivative of f, so that's the tangent to this line multiplied with delta x. So that's the slope of this line is the derivative, and multiplying it with the offset will give us the height of this triangle. And then we can compute the length of this part of the triangle, so of this part, the long side of the triangle, using the Pythagorean rule. So that's just the square root of the sum of these squares. So this delta L is the length of the blue triangle over here. And we can then compute that using this formula as I just explained. And again, if we do this for all these subintervals, well, then this will give us an approximative length that we can sum up. And if we make these intervals smaller and smaller and smaller, these blue triangles, well, at least the long side of these blue triangles will more and more and more approximate the actual length of the curve over that interval. So again, we can compute the actual length L of f of x between a and b by summing up these small areas delta L if we let n go to infinity. So this means that, well, we take the sum of all these small delta L, we let n go to infinity. This again leads us to what we call a Riemann sum, and from calculus we know a Riemann sum is basically a definite integral. So we can directly compute now this length L using information of f itself here. Let's look at a somewhat more applied example. And this applied example, well, let's take a look at the thrust that we get from a rocket nozzle. So a rocket nozzle works as follows. We have some combustion going on here in a combustion chamber, and we have then a certain amount of mass that is ejected from the nozzle at a high velocity. And then Newton's third law will dictate that whatever you expel from the bottom is related to the acceleration that you get towards the top. So that is the thrust that you can expect from such a nozzle. That's the mechanism at how it works. And if the nozzle were uniform, so if the outward velocity of our combusted fuel at the nozzle were uniform with a value of v, and if the density also here were to be uniform, then we can easily compute the thrust, because that thrust, well, using a simple law from Newtonian mechanics, this would end up being rho times v squared, which is related to the kinetic energy that you expel from the nozzle, times the area of the nozzle, pi times r squared. So that would be the case when we have a uniform outflow at the velocity. However, in practice, this is not true. Because of side effects, well, your exit velocity will have a profile, so it will be much larger away from the edges of the nozzle than really at the edge of the nozzle. And also the density will have a profile which is not uniform. So this will also depend on R. So we cannot use this formula over here. However, we can kind of find a way to again use this concept of combining infinitesimally small parts where we can compute the desired quantity and then summing these up over the entire area that we're looking at in order to really compute the aggregated or integral quantity. So what we do is, instead of trying to compute the thrust in one step, well, we calculate the thrust of a small part of the nozzle. So we use an annulus, so a small ring of width dr, which is situated at a radius r. And within this annulus, we assume that this annulus is so thin that the exit velocity is constant within that annulus, as well as the exit density, which is also constant. And what we then do is, again, we take these annuli to be smaller and smaller and smaller. We sum them up over our entire region of interest, and this will again lead us to a integral definition. So this would again lead us to a Riemann sum, which then leads us to an integral. So this is a direct application of a definite integral in, let's say, aerospace or mechanical engineering. Okay, so now that we have covered some applications of definite integrals, why do we even need to bother with numerical integration? Because in calculus, you've learned that in order to compute such a definite integral of a function f, all we need to do is find a antiderivative of small f, capital F, such that the derivative of capital F is equal to small f. And if we have this antiderivative, well, we can simply evaluate it at the endpoints, and that will be exactly equal to this definite integral over here. And that's the second theorem of calculus, the main theorem of calculus, fundamental theorem of calculus. However, as you might agree with me, integration or finding these antiderivatives, which is actually the hard part, is a lot harder than differentiation. Because whenever you're given a function, an analytical function, differentiating it might take you a bit of time, but that's always possible. That's always something you can do, and you can always find that with pen and paper. However, integration is an entirely different story. It's a lot harder, even for simple functions. This might be very, very much harder. Because for very many functions in analytical form, antiderivatives can actually not be found. And some maybe innocent looking functions, for instance, the sine of x squared, an exponential with x squared, or the square root of 1 minus x to the power 4. So these functions do not look very daunting by themselves, but I can guarantee you, if you want to compute these definite integrals, you will have a very hard time, because there is no closed form analytical formulation of these integrals over here. So you cannot simply compute them by hand. On the other side, if you have a tabulated function, so you do not have the function f in an analytical form, but you just have data points, x and f of x, for specific values for x, well, then analytical integration is impossible anyway, and you have to resort to some kind of numerical procedure. So instead, what we do is we approximate such integrals numerically, and that procedure is called numerical integration, but in numerical mathematics you can also quite often encounter the term quadrature, which is a synonym for numerical integration. Some approaches to numerical integration, well, the entire outcome, the entire idea of what will come out as your integration rule will in the end look like this, and the integral will be approximated from the integrand f, which will be evaluated at specific discrete points x using certain weights. So we will come up with some kind of a weighted sum of function evaluations. That's how your integral will be approximated. And the different integration rules, well, they can be distinguished based on which points are selected where you evaluate your function and how the weights or the coefficients that you use to compute this weighted sum are determined. We can distinguish this first based on how these points x1 to xn are selected. And they're again similar to, for instance, solving nonlinear equations. We can distinguish between closed methods where the endpoints are included in the evaluation points. Examples here are the trapezoidal method or Simpson's method, or open methods where these endpoints are not included. And examples here are midpoint or Gauss quadrature, which we will also discuss within this lecture. A second way of distinguishing these methods is how are the weights or the coefficients in this weighted sum actually computed. And the main approach that we will discuss here, so almost all of our integration methods that we will discuss, fall into the category of Newton-Cotes integration formulas. Now, what do Newton-Cotes methods do? Well, actually what they do is they approximate the function f, so this black line, the function f of x, over the integration interval with a function that we can easily integrate. And for instance, most of these Newton-Cotes methods, they will use a polynomial function of a certain degree, zero order, so that would be a constant, first order, that would be a line, or a quadratic function, etc. So we use polynomial functions. And in that sense, well, this red line approximates the black line. And in that sense, well, what you come out with is that the definite integral of f of x, which is something that's either very hard to compute or impossible to compute, that we approximate this with the integral of a polynomial function. And you know how to integrate polynomial functions because those are the easiest functions to integrate analytically. And that's something that we will want to do in those kinds of methods. And we will see more on that in the remainder of this lecture.